are going to have two theorems today that are similar to the two from the other day. A polygon sum theorem and a polygon exterior sum theorem. Polygon, by definition, is a closed plane figure, with at least three segments that are, or three sides that are made up of segments. And the sides intersect only at their endpoints. So a polygon is a closed plane figure with at least three sides that are segments. And these segments only intersect at their endpoints. To break down this definition a little more. Closed means that there can be no open spaces. All the sides have to touch. We can't have a gap or an open space or a crack or anything. A plane figure is two-dimensional. It's flat. So a polygon has to have two dimensions. It has to be a flat figure. So like a dice would not be a polygon because a dice is three dimensions. With at least three sides that are segments. So a polygon starts at three sides. You can't have a two-sided polygon because then it's open. I can't connect them. So you have to have at least three sides. And the sides have to be made up of segments. Segments are straight, which means the polygons can have no curves because they're made up of only segments. So there are no curves on a polygon. And then the sides intersect only at their endpoints, meaning they're not going to cross each other besides at the endpoints. So below I have some different examples. This first figure, A, B, C, D, E, this would be a polygon. It's closed, it's flat, it's two-dimensional. It has at least three segments, and they're segments, they're not curves. And each segment intersects at the endpoint. This is an example of a polygon. The second one, not a polygon, it's open. Third one, not a polygon, because segment CD and AE are intersecting at more than an endpoint. They have to intersect just at endpoints, so this is not a polygon. Not a polygon, it has curves. Not a polygon, it's made up of curves. Polygons have to have straight sides. Not a polygon, because it's three-dimensional. It has to be flat. It has to be two-dimensional. So these would be examples of non-polygons. They're not polygons. After you decide if it's a polygon or not, then you can classify it many different ways. One classification would be a convex polygon, which the book defines as saying it does not have diagonal points outside of the polygon. Convex polygons do not have diagonal points outside. Concave polygons will have at least one point of a diagonal outside of the polygon. Concave polygons have at least one point of a diagonal outside of the polygon. The diagonal of a polygon is a segment that connects non-consecutive vertices. the vertices are the corners of the polygon. It's where the two segments intersect, the endpoints. So a diagonal is a segment that connects non-consecutive, meaning like every other non-consecutive, the one not right next to it. On my figure down here, ADYTR, the diagonals have to connect non-consecutive vertices. So if I start at R, A would be consecutive because it comes right after it. D, I'm skipping it, so here's a diagonal. R to Y, this is a diagonal because they're non-consecutive. But if I do R to T, that's just one side, so I'm not going to create a diagonal there. If I go to A, I'm not going to go to D because it comes right after it, but I can create the diagonal AY and the diagonal AT. From D, well, I already go DR, but I could go to DT. Y already have its diagonals. If a figure is convex, no part of the diagonals are outside of the polygon. That's what they're saying up there. That there are no points on the diagonals that are outside of the polygon. This would be a convex polygon. Nothing, no part, none of the points on my diagonals go outside of that pentagon. This other figure, MPGQSWK, diagonals connect non-consecutive vertices. So if I connect S to W, that's not a diagonal because it's one side. But S to K would be a diagonal. And S to M would be a diagonal. And S to P and S to G. So there's 4 diagonals. Right here, it's outside of the polygon, so that makes it concave. The definition says that a concave polygon has at least one diagonal with points. So just one point of a diagonal outside of the polygon, and this makes it concave. That's how the book describes it. When I describe it, I think science. I think of my lenses. A convex lens is like a dome, like the Dakota Dome in Vermilion or the old Metrodome in the cities. Convex polygons dome out. Concave lenses would be like your contact when you hold it on your finger. It's like a bowl. So concave polygons cave in on themselves. This guy is caving in on itself. This pentagon is convex. It's like blown out as far as it can go. Okay, so you can think of it as the diagonals, how the book describes it, or think of it as convex being like a dome and concave being a bowl. They cave in on themselves. 2 ways to classify a polygon. Other ways to classify polygons. Equilateral polygons. Yesterday, day before, we talked about equilateral triangles. What's an equilateral triangle? Yeah, all 3 sides are congruent. So if I have an equilateral polygon, what do you think you know? All sides are congruent. So you could have an equilateral 5-sided figure, meaning all 5 sides are the same length. If I have an equilateral 8-sided figure, then all 8 sides are congruent. How about an equal angular polygon? What do you think there? All the angles are congruent. Yeah, an equal angular polygon will have all angles congruent. So if it has 8 angles, then it would have 8 congruent angles. Looking at them, maybe they might just do this for equilateral. It won't state it, but it'll just mark them all congruent. Then you should know that's equilateral. An equal angular, it won't always tell you it's equal angular, but if they mark all the angles congruent to each other, then you can conclude it's got to be equal angular. If a polygon is both equilateral and equal angular, then we call it a regular polygon, which means all sides and all angles are congruent. A regular polygon is both equilateral and equiangular. Again, they may not say it in the directions, but if it's marked in the diagram having all angles and all sides congruent, then you would call it a regular polygon. A common example of an equiangular polygon. What is it? A rectangle. All my angles are 90, but my sides aren't all congruent. That would be an equiangular. Common regular polygon? A square. All four sides are the same. All four angles are congruent. That's a regular polygon. So just because the angles are congruent doesn't mean the sides are. Or just because the sides are congruent doesn't necessarily mean the angles have to be. If they're all congruent, then we call them regular. Okay? Ways to classify continue on. You can classify angles based on their number of sides. Most of these you probably have heard and used before. If it has 3 sides, we call it a triangle. If it's got 4 sides, we call them quads, quadrilaterals. 5 sides, pentagon. 6 sides, hexagon. The word 6 is spelled S-I-X. I always remember it because they both have X's in them. 7, heptagon. 8, octagon. 9 is called a nonagon. 10, decagon. And 12, dodecagon. You need to know those words. If I give you a 12-sided figure and say classify it based on the number of sides, you won't write 12 sides, you need to write dodecagon. If it has 11 sides or anything greater than 12, we call it an n-gon. N means the number of sides. So if I said it had 16 sides, then you would write down it's a 16-gon. If it had 21 sides, then we're just going to write 21 gon. They don't have a word for every polygon for each number of sides, so then they just put the number and gon behind it. Over 12 and 11, because we don't have the word for 11, so we call it an 11 gon. So if it was 13 sides, then you just call it a 13 gon. Does that make sense? Riley? I don't really know. I don't know. I haven't really pondered that thought. I just accepted that and moved on. Okay, so there are the different ways you can classify it. If it says classify it based on the number of sides, then you're going to use one of these words. If it asks, is it convex or concave? Well, pick one. If it says classify it based on its angle measures and they're all congruent, then you say equiangular. All right, you need to know all those classifications. We're going to practice here. Number 1, classify the polygon at the right by its sides, then identify if it's convex or concave. Well, if you're going to classify it based on its sides, what are you going to do with the sides? Count them. Good. Did you get 12? What do we call a 12-sided figure? A dodecagon. Dawson? Probably not, but I feel like we should be able to at least spell that one. Do your best.
I forgot the A.
Oh, then we have to decide if it's convex or concave. What do you think? Is it doming out or is it getting caved in on itself? It's caving in. These sides here, they're caving in. Or the diagonal way. If I connect my diagonals, this diagonal's outside of the polygon, so then it's got to be concave. It only takes a part of a diagonal on the outside to make it concave. The whole thing doesn't even have to be out there. Okay, flip it over after you have that written down. Number 2, name the polygon, then identify its vertices, sides, and angles. When we name this, we're going to give it a first name and a last name. Its first name is going to be based on the number of sides. So based on the number of sides, what would you call this polygon? Hexagon. Good. There's his first name. Its last name comes from the vertices, the letters on the outside. So start at any letter. What do you want to start at? A? Sure, it doesn't matter. The part that matters is that you go around clockwise to get back there. Do not skip around. Don't call it hexagon A, E, F, D, C, B. You need to make sure you go in order. So we could call this guy hexagon A, B, C, D, E, F. Bless you. You could start at D, but then make sure you just go in order until you come back there, and you could call it hexagon D, E, F, A, B, C. You just have to go in order. Clean. Sure, you can go counterclockwise. Yep. Just don't skip. There's its name. Identify the vertices. The vertices, you guys, are the corners. It's where the sides intersect. It's a point. Where two lines intersect, it's a point. So what's one vertice? A. Good. That's where these two sides intersect. What's another vertice? E. What's another one? B. Good. Most people would probably put an alphabetical order, but it doesn't really matter. List them. You're listing the vertices. When you list items, you should put commas between them. So make sure you have commas between them. Your English teacher would count it off if you don't put commas where you're listing. The sides. The sides of polygons are made up of what geometric figure? Not lines, segments, right? Good, because they stop. So we need to list the segments. Well, you said it's a hexagon, so it should have how many segments listed? 6. What's one side? A, B. Good. Put your segment symbol on it. Another side? B, C, C, D, D, E, E, F, and F, A. Good. Hexagon, because it had 6 sides. It also had 6 vertices. How many angles do you think it'll have? 6. The number of sides, the number of vertices, the number of angles should always be the same. We've got angle A. What's another angle? Angle B, and a third angle, and a fourth angle. 5th, E, and F. Excuse me. There's like 3 of those on your homework today where you have to name it and then list the vertices and the sides and the angles. To me, it's kind of mindless work, but that way we understand what we're doing. All right. That's kind of handy. I didn't have to draw all those out. Thanks, technology. Okay. My first polygon. What would you call it? Good. How many sides does it have? 3. How many triangles are made? Just one triangle, right? Okay. Can I start at this vertex and draw a diagonal to a different vertex? No, because I only have 2 other vertices, and that just makes my side. So I have no diagonals in a triangle. Tuesday, we learned the triangle sum theorem, which states there are how many degrees in a triangle. All right. My next figure, it has how many sides? So what do we call it? Quadrilateral. Good. From this vertex right here, can I draw a diagonal? Yeah. Can I draw any more from this vertex? Okay. How many triangles are there now? 2. And each triangle has how many degrees in them? 180. So how many total degrees are in my quad? 360. That means the 4 angles on the inside would have to add up to what? No, they'd have to add up to what? 360. All 4 angles would add up to 360. Okay. This next figure, polygon, has how many sides? 5 sides. And if I start just at one vertex, can I draw a diagonal from that guy? Can I draw another one? Can I draw another one? No. How many triangles did I get? Nope, I'm only going from one vertex. You're only doing it from one vertex. So if you're going to go from here, you can't draw this one in. Only doing it from one vertex. You can pick any vertex, but it only goes from one. How many triangles did we get? 3. And each triangle has how many degrees? So how many total degrees are inside of that 5-sided figure? 540, how did you do that? Oh, just add 131, or 180, 180, and 180? Or take 180 times 3, yeah. My next polygon has how many sides? What? Okay. 6 sides. If I start at one vertex, can I draw a diagonal from there? Can I get another one? Can I draw another one? Can I draw another one? From this vertex? No or yes? No. Okay. So how many triangles did we create? And each triangle has how many degrees? So how can I figure out how many total degrees are inside of that 6-sided figure? How did you do that, Wagley? You just know? You added 180 4 times? Oh, yeah, that's a good idea. Just add it to the one I already had. Good. Do you see any patterns? Mason? Okay. Okay, my triangles increase each time by how many triangles? 1. Each time I add a side, I add another triangle, right? Which means I'm adding another 180, because if I add one more triangle, I add another 180. Do you see any other kind? Yeah, don't look across, maybe look up and down. Okay. We'll try.
Okay, so the number of sides and the angles, triangles that are made is 180, how many degrees it is, and then depending on how many triangles are made and the sides.
Okay. I think I know what you're trying to say, but I'm going to let someone else try. And did you want to say anything, Jacob? Brady? You guys had your hands up. How do you know? Oh, okay. Rashid? He said if the figure had 10 sides and you subtracted 2 from it, then we'd have 8 triangles. All the sides that we have so far are 2 more than the number of triangles, or the triangles are 2 less than the number of sides. Do you see that pattern? Looking up and down, 3 sides makes 1 triangle, difference 2. 4 sides makes 2 triangles, difference of 2. 5 minus 2, yeah. Is that where you're trying to go at? Relatively good. That's the other pattern I wanted you to find. Most of you have already started filling out your table. If you haven't, you can fill it out with me, or we can continue. 4-sided figure made 2 triangles, and we said that gave us 360 degrees. A 5-sided figure made 3 triangles, and we said that was 540 degrees. That's the sum of the interior angles. So all 5 angles inside of the pentagon are going to add up to 540. That's what that's telling us. A 6-sided figure, we didn't get there. Did we? Yeah, we did. Gave us 4 triangles, and we said that was 720. They skipped 7. Octagon then should give us how many triangles based on 6, yeah, whatever observation. Can I draw it? All right, hang on a second. Let me extend this out. Let me use my sweet rule. 1, 2, 3, 4, 5, 6. Oh, the triangles and what they create. Okay. All right, so we got 6 triangles. So how do I figure out the sum of the interior angles then? How? You don't know how you do it? God just went, boom, you are going to know these?
So I wrote, yeah.
You showed work?
Yeah. And it's 180, and then in parentheses, x minus 2.
Oh,
X is the angle.
just shush for a second. So to get this guy, we would have to take 6 times 180, which vaguely gave me what? 1080. You mean you just knew that? You didn't even have to do that with your calculator? Decagon, Rashid, would make how many triangles? 8. So then to get all those angles on the inside, I would have to take the number of triangles times 180, because the triangle sum theorem says they have to equal 180. 1440. So if n is the number of sides, then rain, the number of triangles formed would be what? If for n number of sides. Minus 2. So I don't know how many sides there are. There's n of them. So the number of triangles formed would be n minus 2. Yep. And then to get the total degree measures, I would have to take those triangles, n minus 2, times 180. N stands for the number of sides. So if it had 14 sides, then we would say 14 minus 2 gives me 12 triangles. Take that times 180, and that's what all the angles are going to add up to. If you flip your note packet back over to where we started, 2/3 of the way down, Theorem 314, that's what we just kind of created or whatever, went through. Theorem 314 is called the Polygon angle sum theorem, which states the sum of the measures of the interior angles of an n-gon, that's the number of sides, is n minus 2 times 180. You might want to circle that n minus 2 times 180 or highlight it or whatever. N stands for number of sides, which is always the same as the number of angles, bless you, in the polygon. Okay. Now this table, the more you work with these, you're probably going to start to memorize, like pentagons always add up to 540, but I'm not always going to give you a pentagon. I might give you a 17-sided figure. So that's why you need to know this thing, that the number of, or the measure of the angles is the number of sides minus 2 times 180. Exterior angles are found where? On the outside. So if I take this giant octagon that I have up here, exterior angle is formed by one side and the extension of another one. So here's one exterior angle. One side and the extension of another one. There's another exterior angle. One side and the extension of another one. One side and the extension of another one. One side and the extension of another one. One side extending the other one. One side extending the other one. One side extending the other one. Okay, so at each vertex, I really have 2 exterior angles, but we only want to use 1. Because remember yesterday we talked about how the exterior angles are vertical. so they're going to be congruent anyways. So we only need to worry about one at each vertex. These exterior angles, they go around my figure. What shapes are round? Circles. How many degrees are in a circle? That's what the exterior angles add up to. All 8 of those exterior angles will add up to 360. All three, because it's a triangle, exterior angles are going to add up to 360. It doesn't matter what type of polygon it is. The exterior angles will always add up to 360. The way I remember that is because they go around the figure. That's your other theorem there on the front side, the Polygon exterior angle theorem. The sum of the measures of the exterior angles in a polygon is 360. Some exterior angles will always be 360. Okay. Using the classifications and these theorems, we're going to go through a few more examples. So go to number 3. It's going to have to probably flip back. It's like 2/3 of the way down on that side. And it says find the measure, oh, just kidding. It says find the sum of the measures of the angles of a decagon. Okay. Whenever it says find the sum of the measures, you're thinking about that interior polygon theorem, that the sum of the interior angles is n minus 2 times 180. N in this theorem stands for what? Number of angles or the number of sides, right? In a decagon, how many sides are there? 10. Just like in a decade, there are 10 years. Deca means 10. So then we're going to say 10 minus 2 times 180 is how I find my interior angle measures. 10 minus 2, because it's inside of the parentheses, is 8. And then 8 times 180 is, what do we say again? 1440. So all 10 angles inside of the decagon will add up to 1,440 degrees. That's what that number is telling us. Like I said, you're not always going to get ones from the table, so make sure you understand n minus 2 times 180. Number 4, find the measure of angle x in the quadrilateral. Here's angle x. I don't know what it is, so I'm just going to call it x. I'll just give it that variable. But we do know that angle W is 100 degrees, and angle Z is what? 90. How about angle Y? What's Y? It's congruent to x. So if x is x, what's Y? X. They're congruent. We don't know either of them, but we just know they got to be the same. Add them all and set them equal to 180. Equals 360 because it's a 4-sided figure and all 4 angles have to add up to 360. Hopefully that one we usually know. So yeah, 2x, because I have 2 of them, plus 90 plus 100 has to add up to 360. All quads add up to 360. 2x plus 190 equals 360. How do I bring my 190 over? Subtract it. 170. Divide by 2. And what do we get for x then? 85. And x represented the measure of my angle x. So we can say the measure of angle x equals 85. All right. Number 5. Classify each polygon by its sides and then identify each as being convex or concave. So go ahead, take a minute here. 6. Hexagon. You can check with the diagonals. None of them are on the outside, and no parts of them are. So then this is a convex polygon. None of the diagonals are on the outside. It's like it's domed out. The second one. 7, 8. So this would be an octagon. And if we check with the diagonals, oops, that's not diagonal. Oh, that one's, they're all inside. There, outside. Since this one is on the outside, what do we call it then? Concave. Or you can think that this side is caving in on itself. The polygon is caving in. Questions? Okay, that's all we're doing today for notes. Here is your homework, page 161, 1 through 15.